Lab 4. Oscillations. The purpose of this lab was to analyze the motion of a spring mass system and create a computer model that predicts the motion of a mass swinging in an arc while oscillating on the spring by using the energy principle as well as the momentum principle, or Newton's second law. So a quick overview of the results. The spring mass system satisfies the energy principle. Also, the computer model accurately predicted the observed motion of the mass. Some discrepancies between the computer model and the observed data resulted from the drag force that we assumed was negligible, as well as through a round-off error that was caused by using Microsoft Excel when I was transferring the data into a CSV file. In order to accurately predict the motion of the mass, we need to specify the net force acting on the system by accounting for all the interactions of the mass with the surroundings. This includes both the weight force mg and the spring force negative ks. At the beginning of the video, the mass is hanging motionless. When the mass is pulled down and released from rest, the mass oscillates in both the x and y directions. After analyzing the video and tracker by setting the length scale, coordinate axes, and stepping through each frame of the video, I was able to create a spreadsheet of x and y positions. This file was read into my code and compared to the motion predictions of the computer model I created from the initial data of the mass. The mass was given 0.402 kilograms, with an initial position of negative 0.118, negative 0.634 meters, and with an initial velocity of 0 meters per second as it was released from rest. Using this information and the graph of the oscillation, I was able to calculate the period of oscillation, which I found to be 1.62 seconds. I did this by calculating the average of 3 observed oscillations, so I found the interval of 3 oscillations and then divided by 3. Then, by rearranging the formula for T, I solved for the stiffness K and found a value of 6.047 newtons over meters. This is seen in the equation on the right side. Another variable that I needed to calculate from observing the motion was L0. L0 is the relaxed length of the spring and can be calculated under the assumption that the gravitational force is equivalent to the force of the spring, because the spring would be in static equilibrium. By breaking down the stretch into L minus L0, we can solve for L0 because we know that L is equal to 0.7 meters, and we have already solved for K and can easily compute the gravitational force on the mass. From this process, I was able to calculate L0 to be equal to 0.0485 meters. Taking these calculations and inserting them into the Python code, as well as applying Newton's second law to predict the motion of the mass, we can compare the computer model of the motion of the mass with the observed data. While the weight is constant, the spring force gets smaller as the stretch gets smaller and larger as the stretch gets larger. F net equals gravitational force plus spring force. The fundamental principle that is most important in this lab is the energy principle, or delta E equals work. Delta E is the change in the total system energy. In order to examine this principle, we need to establish that the system in this case includes the mass, the spring, and the earth. This is important because both the spring and the earth have corresponding potential energies that will factor into the description of the system. To expand on the energy principle, we must set up the equation that delta E is equal to delta K, the change in kinetic energy of the mass, plus delta U sub G, the change in gravitational potential energy, plus delta U sub S, the change in spring potential energy. The main idea of the energy principle is that the total change in energy of the system must be equal to the total energy transferred to and from the surroundings. But because we chose the system to also include the earth and the spring, there are no interactions that transfer energy between the system and the surroundings in this case. This is only true if we neglect interactions such as air resistance. The attachment point also does not cause energy transfer because it is motionless, so no work is done. Thus, we can see that the extent in the Python code, I inserted the respective equations for each component of delta E prior to the while loop and within the while loop because we need to calculate the components at each iteration as these values are changing based on the position of the mass. You can see where the momentum principle is applied in these two lines here. To calculate the change in kinetic energy, gravitational potential energy, and spring potential energy, I inserted the equations such as 1/2 mv squared for kinetic. This line creates a red ball that is a visual representation of the position data observed from tracker and inputted from the CSV file. In the graph, delta U sub G is in green, delta U sub S is in red, delta K is in blue, and delta E is in yellow. The sum of all the changes, delta E, is equal to 0. As we predicted from earlier discussions of the energy principle, delta K, shown in blue, decreases as time goes on because the velocity decreases. Delta U sub G stays constant throughout, and delta U sub S decreases at first, but then increases to make up for the decreasing delta K. For the what does it mean questions, as I just discussed, the energy principle is satisfied because energy is conserved and delta E is equal to 0. This is because no energy is transferred between the system and the surroundings. The period of oscillation is larger in the x direction than in the y direction because there is more movement in the x direction than in the y direction. The difference is because distinct equations are used to calculate each period. The oscillation in the y direction was 1.62 seconds and 1.68 seconds in the x direction. So these two equations were used for the respective directions of the oscillation. So the red ball is the observed data and the blue ball is the predicted data. So at first the red ball and the blue ball match very well and the model is predicting very accurately, but as time goes on, the pathway of the observed data begins to slightly change from that of the model data, potentially because of air resistance that we assumed was negligible or because of round-off errors that occurred through Microsoft Excel. Thanks for watching.